Today we're solving LeetCode 3454, Separate Squares 2. This problem tests binary search on the answer combined with sweep line and segment tree, a core pattern for advanced geometry interview questions. You are given multiple axis-aligned squares on a 2D plane. Each square is defined by, here, x, y represents the bottom left corner of the square, and L represents the side length. All squares may overlap. You must find the minimum y-coordinate of a horizontal line such that the union area of squares below the line equals the union area of squares above the line. Important constraints. Overlapping areas are counted once. The line may cut through squares. Partial areas count. The result must be accurate within 1 times 10 to the power of -5. Imagine 2 overlapping squares. We draw a horizontal line at some height. We set y equal to mid. For each square, part of it may lie below the line, part may lie above, or it may be entirely on one side. The key detail: when squares overlap, their shared region must only be counted once. So visually, we slice the plane horizontally. Measure the union area below the slice. Compare it with the union area above. Our goal is to slide the line until both areas are equal. This problem combines 2 patterns. Keycap 1 binary search on answer. As the horizontal line moves up, area below increases, area above decreases. The function compute the union area below the line at y is monotonic increasing, so binary search applies. Sweep line for union area. To compute union area correctly, overlaps must be merged. This requires a sweep line plus segment tree. This is the critical difference from separate squares I. Let's try a brute force approach. Naive idea. For every possible y, compute the union area below. Stop when it equals half the total area. Why this fails? Infinite continuous y values. Union area computation is expensive. Completely impractical. For optimal solution, step 1, binary search bounds. The lower bound of our search is the smallest bottom edge of any square, and the upper bound is the highest top edge, which is y plus L. Step 2, helper function. Compute union area below a given mid. We do this using a vertical sweep line. For each square, we first compute the vertical contribution below the line at y equals mid. The height is the difference between mid and the square's bottom edge, clamped between 0 and the side length. If this height is greater than 0, we generate x events by adding an interval from x to x plus L with that height. Step 3. Sweep on x-axis. Sort x events. Use a segment tree over y intervals. Track total covered vertical length. Accumulate. Multiply the covered height by delta x to get the area of this segment. This gives union area below mid. Step 4. Binary search decision. If the area below multiplied by 2 is less than the total union area, we move the lower bound up. Otherwise, we move the upper bound down. We repeat this process for about 60 iterations to achieve the desired precision. We define a class called solution. Inside it, we define a function named separate squares, which takes a list of squares as input and returns a float. First, we build events and record all x coordinates. For each square with bottom left corner at x, y and side length L, we create 2 events. One for adding the square at y, and one for removing it at y plus L. We also collect all x coordinates of square edges. Next, we sort the unique x coordinates and map each x to an index for segment tree usage. We initialize arrays count and length for a segment tree, which will help us efficiently compute covered horizontal lengths. The push-up function updates the length of a node in the segment tree. If the count at the node is greater than 0, the length is the full segment. Otherwise, we sum the lengths of its children. The update function modifies the segment tree for a given interval QL. Q are by adding or removing coverage, and then pushes up the changes. We sort the events by y-coordinate. In the first sweep, we compute the total union area. We track the previous y, and for each event, compute the vertical distance dy, multiply by the current covered length, and add to the total area. Then we update the segment tree according to the event type. The target area is half of the total union area. For the second sweep, we reset the segment tree arrays and track the accumulated area. As we process each event, we check if adding the current rectangle would reach or exceed the target area. If so, we return the previous y plus the fraction of the vertical segment needed to reach the target. Otherwise, we add the current segment's contribution to the accumulated area and update the segment tree. If we finish processing all events, we return the last y. This method efficiently finds the horizontal line that divides the total union area of all squares in half, using a sweep line algorithm combined with a segment tree. Time complexity, O of log p times n log n. Binary search times sweep line with segment tree. Space complexity, O of n. Events and segment tree storage. Common mistakes and edge cases. Counting overlapping square areas multiple times. Forgetting union logic. Incorrect segment tree interval updates. Using integer math instead of floats. Too few binary search iterations. Wrong search bounds. This problem combines binary search on a continuous answer with union area computation using sweep line and segment tree. Key interview insight. If shapes overlap and area is involved, assume union area unless stated otherwise. Recognizing this distinction is what separates mid-level from senior-level solutions.